So, welcome back to this class. So, we closed the last class with the action potential of mostly the neurons, and I promise you that I will talk about the action potential of the cardiomyocytes. So, when we talk about the cardiac cells, we observe something very unique. If this is the graph what we have been drawing, where you have time in milliseconds and voltage in millivolt, and we see 10, 20, 30, 40, 50, 60, 70, 80, 90, and we see the neurons overshooting, comes back, and then something like this. For the cardiac, we saw a different trend. For the cardiac, what we see, for example, move like this, they remain like this, then they come back like this. So, you see a very unique kind of a plateau here, or sometimes this plateau could be like this, sometimes it could be like this, depending on it has a different kind of slope. What does that mean? Now, going by the simplistic manner, say that this can only happen when there are inside the cells, there are more cations prevalent for a prolonged period of time, right? Then only you will get this kind of things. Interestingly, in cardiac, that is what happens. There is a prolonged period of cations, but which cation? We have already talked about sodium, we have talked about potassium. Which is the other cation there? Now, this brings us to all the previous classes where I told you something. I will take you back, that will remind you what I was trying to tell you guys. I told you that calcium, I told you that this is one ion. I am not talking about it because inside the cell they store the calcium, or else it can become cytotoxic, or it can become excitotoxic precisely. It can lead to extremely hyperexcitability. Now, having said that, I did not explain what all roles it play. Now, I will explain it. What it does is, at this time in these cardiomyocyte cells, they have a very well defined structure called sarcoplasmic reticulum. It is present in every cell, but in the cardiomyocyte it is very pronounced, and they have a lot of calcium pumps and voltage gated, VG stand for voltage gated calcium channels. It is interesting, at this phase cardiomyocytes secrete momentarily, very momentarily secretes a lot of calcium and pull it back. It is like a sponge. You have seen in the kitchen those sponge what you use for cleaning the dishes. It's almost like this. Squeeze it and leave it, pull them back. Because of that spiking of calcium ion here, there is a small spike. So, that generates something we call as calcium spike or calcium current, which leads to this plateau state of the cell. So, now we introduce the third component to the game, or fourth: sodium, chloride, potassium, calcium. It's pretty much these are the common ions which dictate terms in terms of generation of action potential. In terms of pacemaker cells, when we talk about, they follow a different pattern. These are, since they are already sitting at minus 40 millivolt somewhere, minus 40, this is not the minus 40, this is minus 20 I am showing, but just assume that this is minus 40 millivolt. Right? They shoot up this because of there is a very special kind of calcium channels which are present. I am not getting into the details of it, but they do not need that sodium. It is the calcium which plays this critical role of spontaneous action potential shooting. And the pacing of our heart, that process of what you see in an EKG, many of you have seen that EKG traces of that EKG trace, sorry, this is EKG trace, what you see is paced by these pacemaker cells. So, this is the minimum you have to understand about the concept of action potential. Now, I will take you to the next issue about it. Now, we talk about, think of a excitable cell setting. And I told you there are multiple players, sodium, sodium, sodium. They can enter through voltage gated sodium channels, voltage gated sodium channels. Then you have potassium, which will go out by potassium, which are going out using voltage gated potassium channels, and there are pumps. And we are already aware of the fact that outside to inside voltage is minus 90 or minus 70 millivolt. We are not talking about the pacemakers, we are just talking about the regular other excitable cells. Now, think of an imaginary situation. If synthetically, by your own process of electronics, you could bring the cell, you could change the voltage from say minus 90. So, if you give a voltage pulse like this, minus 90, minus 80, minus 70, minus 60, minus 50, minus 40, minus 30. And if these are those pulse line, of course, you decide the time up to what space you are giving the pulse, you can activate these channels because they are function of the voltage across the membrane. So, in a synthetic manner, you can actually activate these channels which otherwise are activated by the ligands when something binds to them. It could be a light as photons, it could be something like acetylcholine, a neurotransmitter, it could be a toxin which opens them up or close them up. It could be something like tetrodotoxin, which is a bioterrorist agent, TTX. Okay. Look for this. What is this? It's a sodium channel blocker. Now, these are some of the very potential bioterrorist agent, sodium channel blockers. Okay. Then similarly, you have curare. These are neuromuscular junction. NMJ stand for, N stand for neuro, M stand for muscular, J stand for junction. These are neuromuscular junction blockers. Okay. There are a series of such blockers which are very, very potential bioterrorist agent. You can actually paralyze a whole population with these kind of toxins. Now, how you test them? Now, that brings us to the very beautiful part of the biosensing. Now, I told you that you can actually study these ion channels by varying the voltage. Now, those of you who are having some background in molecular biology, they know that you can express these channels using molecular biology tools in a larger number. You could have cells only with sodium channels. You could have cells only with potassium channels, because you could manipulate the DNA and express them in some other species or some other cell types, and you can study these channels, because these channels are the real sensor elements. Okay. Now, having said this, we will talk about how you can measure. So, when we are talking about an action potential which shapes like this, where you are seeing the 0 is, this is the 0 line and this is minus 80 millivolt line. So, it means this event is being conducted by 3 different kind of currents. Potassium current, sodium current, and of course, the pump. How we could measure these currents? These currents are nothing but these are fluxes, right? Now, that brings us to 2 different words of whole cell biosensors. One is voltage clamp, the other one is current clamp. And the technique which falls under this is called patch clamp or even intracellular recordings. Okay. What is voltage clamp? When you talk about a clamp, clamp means you are holding somebody. If you hold the voltage, then you can read the current, because we all know about the Ohm's law, V is equal to IR. So, you fix the voltage, you know the current, or you fix the current, you can read the voltage, right. So, when you are seeing the change in the voltage out here, that means you are fixing the current. That means what you are seeing so far is current clamp. You are fixing the current and you are seeing the change in the voltage. Now, could you do the reverse? Where is a voltage clamp? If you could do the voltage clamp, then you will be able to read the current. How you could do the voltage clamp is, say for example, here you have a cell, okay, sitting there. It's a given assumption, this is a electrically active cell, and you have a electrode sitting like this, and you have a ground electrode sitting like this, and you are measuring the current across it by fixing the voltage. Fair enough. Now, this cell is sitting at minus 80 millivolt, that we already know. Okay. Now, what you do is you decide a current voltage shift. You are fixing the voltage. Now, it is sitting at minus 80. Then you give a pulse of say minus 70. Then you give minus 60. You can change this pulse. You can make it minus 75, minus 65, depending on. I am just making it, trying to make it simple. I am just giving a step of 10 millivolts. So, you are varying the voltage. So, you are fixing the voltage at different point. And this is the time. So, you are giving different kind of pulse, and what will you observe is up to this zone somewhere you will observe there will be this unique current which will be shifting its value, eventually will wind up, followed by in a time frame. If this is what is y axis is showing you the now the current, not the voltage anymore. Okay. Next, it will be followed by the time window. You will follow appearance of another set of current, which will increase, 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 and then it will. This first set of current, what you see with respect to time, is sodium current. Second set is the potassium current. Of course, they have a different directionality. I am just putting as the function of time, but if you want to change the directionality, you can make it like this. You can just reverse it. So, in a space time, sodium wave coming from outside to inside the cell followed by a potassium wave. They are going from inside to outside the cell, and you can exactly do this. This was feasible because of a technique called patch clamp technology, which was a baby of 1960s and 70s, mostly. I mean, and this was again done in Germany. Erwin Niher, Bert Sackmann, Alan Marty. There are other people who are involved in it. Niher and Sackmann won the Nobel Prize for this work, discovering patch clamp, which is improvisation and getting fantastic recording of voltage clamp. Prior to that, it was all current clamp, where we were seeing the change in the voltage. And soon you will realize what are the different ways you can study an excitable cell. That brings us, because this is a critical juncture. It completely changed the complexion of the field, and it took the field by a stride. For this particular work, they won the Nobel Prize. It changed the whole field, because prior to that, it was not possible to get the values, though we were explaining all the action potential, but to measure the sodium current and potassium current separately, and their polarity and directionality and all those things was not feasible. So, all the studies were mostly revolved around current clamp. You are fixing the current and you are seeing the change in the voltage. So, I was repeatedly telling it is in millivolt. Voltage clamp, this changed everything, and that opened the whole field of voltage gated ion channels. So, this particular conformation. So, if you look back the whole last century of developments, there are different kind of conformation of electrodes which were being used. Okay. So, if this is the cell we are talking about, one conformation is intracellular conformation, where your recording electrode is inside the cell, and of course, you have the ground electrode, which is I am just showing it like this, and you are measuring the value across this. Conformation 1. Second conformation was, this is conformation intracellular, where the electrode is inside the cell body, the nucleus and everything, right. This is the first conformation. Second conformation, a modification of this conformation, a more improvisation of this conformation is, which is also falls under the intracellular, is the patch clamp conformations. And in the next class, we will talk a little bit about patch clamp conformation, followed by the other conformation of the same time prior to patch clamp was extracellular conformation. And from there, we will move on to micro electrode array and planar patch clamp. And another side we will open up will be FET, field effect transistors. This is how our next set of investigations will proceed. Thank you.